So now we finally move on to proton NMR. And while this is the last of our major spectroscopic techniques we're going to cover for right now, it's by far the most important. And the reason that it's the most important is that it has the most information available to us from a single technique. That's because in addition to giving us the same type of information that we get from a carbon NMR spectrum, that being the chemical shift, helps us to determine the environment that hydrogen is in, proton NMR also gives us a lot of information about how a molecule is actually put together. And so those two items are what make this the most powerful technique that we have. So we're going to start by talking about chemical shift. But again, I want to emphasize that what we see from chemical shift in proton NMR is very, very similar to what we saw in C13. Now, what do I mean by that? Well, overall, what I mean by that is that, first of all, we use the ppm scale. TMS is a reference compound, which is again set at 0 ppm, just like in carbon NMR. And again, low electron density, high chemical shift, which we abbreviate with this lowercase delta, high electron density, gives us low chemical shift. Now, just like with carbon NMR, we have the same types of relative shifts that we can talk about based on what the functional group is. And we'll see some examples right here. Let's bring that information in a different way. So there's the first half of our chart. And there's our second half. So possibly the first thing you might notice is the fact that whereas carbon NMR went from 0 to about 220 ppm, the range for proton NMR is only from about 0 to 14 ppm. Now that doesn't really have any major impact on it, just sort of something to keep in mind. And in fact, the range is actually a lot smaller than that. I'm going to highlight a couple of functional groups. That's the aldehyde and the carboxylic acid. Those are really the only functional groups that show up above about 8.5 ppm. So it's very nice. When you see a peak in this 9 to 10 range, 99% of the time it tells you have an aldehyde. And same thing with this 11 to 12 range. Anytime you see something above 10 ppm, you can be about 99% certain you've got a carboxylic acid. You can also see other examples of where peaks show up. Our hydrocarbon peaks are all fairly low chemical shifts, 1 to 2. As we start adding other functional groups nearby, such as carbonyls or aromatic rings, we get above 2 ppm. Nitrogens and halogens will push you up, or oxygens will push you up, 2 to 5 ppm, and so on. Possibly the most difficult functional group to identify here from its range are OH and NH protons. And there's other reasons for that we'll get into later on. But one of the big reasons you can see here is they're pretty big ranges, especially when you look at that mean, 0.5 to 4. That's almost a third of our entire range for proton NMR. So those two groups, the OH and NH protons, are very, very variable within a molecule. But that's okay, because these are two groups that are very easy to identify, as we've seen in IR. So just to sort of summarize this first piece, very, very similar to what we saw in carbon NMR. The chemical shift is determined by the environment that a proton is in. Now, if chemical shift was the only information we got from proton NMR, we'd be done here and we could move on to other things. But let's look at a spectrum. And I'm going to start with a nice simple molecule, chloroethane. Let's draw it out completely. So if you were going to think about a proton NMR spectrum of this molecule, what would you expect to see? How many peaks? So my expectation would be these two hydrogens are equivalent, and these three hydrogens are equivalent, but they're not equivalent to each other. So we have two different hydrogens in this molecule. So let's look at the spectrum. And here it is. Now there are certainly two spots where we have stuff in this spectrum, but if you look very carefully, this first peak, which you probably guessed, and let's put the structure back up here, because that's the first thing we should do, is which proton correspond to which peak. So I'm going to label these as HA and these two as HB. So HB are the protons that are on the carbon next to that has the chlorine attached, whereas HA is further away from the chlorine. So which one's going to be at higher chemical shift? Well, it's going to be the ones that have the electronegative atom attached. So we have HB here and HA here. But if you look carefully at each of these, you'll notice this peak for HB isn't just one peak, it's 4 peaks. Same thing for HA, it isn't one peak, but it's actually 3 peaks. So why 2 sets of peaks here? Instead of just 2 simple peaks, why so many peaks? So before we can answer that, we're going to look at a different spectrum. And we're actually going to look at several of them. So let's start with this spectrum. So still an ethane derivative because we have 2 carbons, but now we've replaced all but one of the hydrogens with chlorines. So I'm sure you would guess fairly logically that we'd only have one peak given that there's one hydrogen, and it's right here. It's at very high chemical shift because we have so many electron withdrawing groups in this molecule. And that showed up at about 6.1 ppm. So now we're going to take this molecule and we're going to replace one of these chlorines over here with another hydrogen. What do you think that'll do to the spectrum? Well, here it is. So 2 things should occur to you. First of all, this molecule is still symmetric. So these 2 protons are equivalent to each other, so they show up as the same peak. Second thing is, you may notice we went from about 6.1 ppm to just below 6 ppm. And that's because we lost an electron withdrawing group. So that makes sense. So nothing funny going on here yet. Now I'm going to replace a second one of these chlorines. I'm going to replace it with a fluorine. And let's see what happens. I'm going to label them as HA and HB. Now I think we can see here fairly easily that HA is not equivalent to HB. And that's because one of them is on a carbon that has 2 chlorines, while the other one is on a carbon that has 1 chlorine and 1 fluorine. And so this molecule is not symmetric anymore. We can also see fairly easily, well, let's ask this question. Which peak is going to be at higher ppm, HA or HB? So HB, given that it's attached to the carbon with the fluorine, which is the more electronegative element, will be the proton that's at higher chemical shift. But now there's another question. Each one of them is showing up as 2 peaks. Why is that? Now we need to get into a little bit more of the theory with NMR. And the piece we need to know is that when magnetic field is applied, each nucleus behaves like a tiny magnet. And when this happens, so here's our proton, or our nucleus. We start out with them sort of aligning in any direction in terms of their magnetism. But once we apply the magnetic field, they have 2 choices. They can align with the field, and they can align against the field. And these are the only 2 options. Alright, so now what happens is an atom, for NMR conditions, interacts with protons that are on the same carbon or on an adjacent carbon. Now, the first situation on the same carbon, we're not going to worry about that one today. That's something we're going to come back to later. Because this only applies if the two protons are not equivalent. If the two protons are equivalent, then none of this matters, which is why when we looked at this spectrum, notice that there was no splitting of this peak. And that's because these two hydrogens were equivalent to each other. So right now, we've only discussed situations where hydrogens that are on the same carbon are equivalent to each other. Later on in this course, when we discuss stereochemistry, we will learn about examples of two hydrogens that are on the same carbon that are not equivalent to each other. But today we haven't done that yet. So we're just going to concern ourselves with this one on an adjacent carbon. So what we mean by that, these two protons would be considered adjacent to each other. Why is that? Well, there's two ways we can think of it. One is that we can count the bonds between them. And so adjacent hydrogens have 3 bonds between them. And that's probably the easiest way to think about it. But we can also think about it in terms of the carbons. So if two carbons are bonded to each other, then their hydrogens would be considered to be adjacent. Alright, now why does this matter? Does this explain why we get 2 peaks for each hydrogen instead of just 1? Well, let's look at this molecule again. So let's consider HA. HA is influenced by any adjacent hydrogens, which is, in this case, HB. Now what can HB do? HB can align with the magnetic field. Well, as a result, this reinforces the magnetic field. Because it's reinforcing the magnetic field, it means we actually need less energy in terms of what HA needs. Well, less energy is what we have when a proton or carbon is de-shielded. And if it's de-shielded, that takes us to higher ppm. So again, let's go back through this. HB is the adjacent proton to HA. If HB aligns with the magnetic field, which is one of its 2 options, it reinforces our magnetic field. if the magnetic field is reinforced, that requires less energy. And if it requires less energy, then we move to higher chemical shift. So then, is the opposite also true? So HB can align against the magnetic field. Well, if it does that, this diminishes the strength of the field. By diminishing the magnetic field, we essentially make it weaker. That means we need more energy. And if we need more energy, that's similar to shielding an atom, and we end up at lower chemical shift. So by having one proton that is adjacent, we split HA into two peaks, which we would refer to as a doublet. And so if we now go back up to that spectrum, again we're looking at HA. HB aligns with the magnetic field. Less energy is needed. We get HA peak at higher chemical shift. When HB aligns against the magnetic field, we need more energy, and we move HB or HA to lower chemical shift. And so we end up with two peaks here. The same thing happens for HB. HA can align with the magnetic field. HA can align against the magnetic field, which gives us two possible peaks for HA, or for HB as well. So overall, what's going on here is that in proton NMR, a hydrogen's peak can be split into multiple peaks by what's next to it. Why didn't we see this for carbon NMR? Well, in carbon NMR, and we can just use the simple example of ethane, we're looking at C13. Well, remember, carbon-13 is only 1% of the natural abundance. So there's a 1% chance of this being C13. There's a 1% chance of this being C13. How often do we get both of them as C13s? Well, statistically, it would basically be 1% of 1%. Or in other words, it's extremely rare, because that would take us to 1 in 10,000 molecules would have two C13s next to each other. So it's not that this type of issue can't arise in carbon-13. It's just it's so exceedingly rare we don't have to worry about it. Now, if we go back to that spectrum for chloroethane, where we had even more peaks, why is it that this one is so much more complicated? That we have 4 peaks and 3 peaks. Well, that's because there's more protons involved. And I'm actually going to pick this example up in the next video because I'm up to almost 25 minutes, and in general I like to try and keep these videos not being too large. So we're going to, in the next video, get into some of these more complicated examples of what we call splitting.